Good morning, my students. Today we begin a new unit about optics and the aspects of light. Especially, we have to study this today the diffraction of light. First of all, what light is. Light has a big history. 1665, Newton proposed the corpuscular nature of light. So, with Newton, light is formed of small particles. 1801, Young explained the phenomenon of interference by means of the wave theory of light. Interference, which will be uh, the object of our next lesson, next chapter. Uh, Young considered that light is a wave. Maxwell in 1876 derived his famous equations and considered that light is a wave, and he proposed the oh, that light is an electromagnetic waves. In 1888, Hertz verified Maxwell's theory, which is a big deal, and considered that light or electromagnetic waves cannot propagate, cannot produce only if charged particles oscillate. In 1905, Einstein rehabilitated the corpuscular nature of light and introduced the concept of photons. For the first time, Einstein called the particle of light as photons. In 1920, de Broglie reconciled the two theories and introduced the concept of the dual nature of light, particle and wave. From 1920, we consider that light has two aspects, one of them particular aspect, the second is wave aspect. Now, before starting the lesson, wave aspect of light, diffraction, keep in mind these important prerequisites. Types of waves. According to their nature, waves are classified into mechanical wave, which needs a material medium to propagate, like sound, water wave, and so on. Electromagnetic wave, it does not need a material medium to propagate. It can propagate in vacuum. Visible light, radio wave, ultraviolet, X-rays are examples of electromagnetic waves. And wave properties. Uh, the main important quantities which are used to describe periodic traveling wave, wavelength, lambda, frequency, nu, this symbol called nu, speed v, amplitude a, and period t. The relation between the wavelength, lambda, speed, and frequency as follow: lambda equal v over nu over frequency, or we can write it v, velocity, speed, equal lambda times frequency. V depends only on the medium of propagation. V depends only, our frequency depends only on the source of the wave, and lambda depends on the source and on the medium. All electromagnetic waves propagate in vacuum or in air at a speed c equals 3 times 10 to 8 meter per second. So lambda air equal c over frequency. Keep in mind also that the frequency doesn't change when propagating from one medium to another medium. The range of light wavelengths in vacuum is, when we call light, we mean the visible light, only the visible light. So lambda in vacuum lies between 400 nanometer and 800 nanometer, and the range of the wavelengths of audible sound in air is at 20 degree is lambda 1.7 centimeter, 70 meter. It's a big difference between light and sound in their wavelengths. If the angle theta is small, mathematical recall, when theta is very small than 10 degrees, then sine theta almost equal theta and tangent theta almost equal theta, or where theta is expressed in radian. To recall the definition of wavelength and the period, here is the simulation fit. Now this is a string. This is a generator of wave, vibrator. Look at this one. Each grain particle of the string uh, vibrates in its place. It accomplished one complete cycle. I begin from here. Look at this one, step by step. Quarter of cycle, half of cycle, three quarter, and one complete cycle. This cycle is completed during one period. At the same time, one period, the wave travels one wavelength. Look at this one. Look at this crest propagating. Okay, again, step by step. This one accomplished. Okay, so the distance from this crest to that is called the wavelength. Follow me in the next video to explain diffraction, and that diffraction defeats the rectilinear propagation of light.